So first of all, your let's call it your first real homework is up. I put it up a little bit ago. We're going to be working through a tool called Mendix. So I'll actually bring it up on here. We're going to be using a tool in here called Mendix initially, and then we're going to be using Python. All right. So there's this kind of long-winded kind of tutorial you're going to go through with Mendix that in the end is going to take somewhere between 8 and 10 hours. I'm going to give it to you in smaller chunks over several homework assignments, and then in the end you'll take a exam through Mendix to get officially certified. You'll be able to throw that on a resume and things like this. So in any case, Mendix. Their goal is what's called a low-coding software environment. So it's a tool that allows you to they have a desktop modeler as well as a web-based modeler that allows you to create web-based and mobile applications and host it on their server for database and all this stuff. So you're going to kind of learn about those pieces without writing a whole lot of code. But you'll be learning about a lot of the problem-solving programming stuff that we're going to be talking about. All right, so if you remember back to the first couple days of class, we mentioned that one of the problems of why programming is kind of hard to learn is human beings are so good at solving problems that we have trouble breaking the problems down into those little steps to articulate the solution. Well, now when you're first learning program, that problem is then learning to program. That problem is then compounded because now you're learning this crazy new language with weird syntax. Now, having said that, Mendix, being a tool, has its own learning curve associated with it. So think about it like having to learn Microsoft Word or something like that to do things the Mendix way. But at the very least, from our perspective, it allows me to introduce some topics that go into the larger software development world without focusing too much on syntax initially. So it gives us probably about a 2 or 3 week period to really introduce the larger range of computer programming and software application development, and then we get into Python and start dealing with the scarier stuff after you kind of have the background knowledge for the bigger tool. Now, what's really nice about Mendix, and the reason that I use this, I'm doing some research with the company right now, is this is kind of the first tool I've run into that actually allows you to create what I would call professional level final products. Where you might actually choose as a company to use the Mendix platform to create a solution as opposed to writing a native iPhone or a native Android application, something like that. Their tool does enough stuff, enough fancier stuff, talking to third-party APIs and things like this that we'll talk about, that you can solve real problems using it instead of it just being like, oh, I want to write a quick little application that, is equivalent to a mobile app or a website for my business. It does more than that. All right. So this is kind of a cool tool that having this background might benefit you in the future. I know we have a couple of students in senior seminar this semester who are IT majors. So only 25% of their project in senior sem needs to be creation, needs to be programming based. And they're using this platform to create the programming aspect of their final solution. And then the other aspect, for example, one of the students in there is working on a digital sign that would go in the back of like your car. So, like you cut somebody off or somebody has their turn signal on or something like that. You want to say, oh, I'm sorry, or your turn signal's on. So this thing will be in the back of your car. You'll have a mobile app that talks to that thing through Bluetooth, who actually is talking to a Raspberry Pi through Bluetooth, and you hit a little button on the app that sends different messages, I'm sorry, or maybe it's a middle finger or whatever, whatever it is, so he's building that system and he's using this platform for building the mobile app side of things because that's not really a strong point for him. And it'll allow him to create a more professional software product without having to deal with kind of his weakness, which is writing native code. This allows you to accomplish some stuff beyond that. So what I've given you for your first assignment, I've given you a link that goes into, let's see, I think it's under, I gave you a link directly to it. In any case, it's like, there's like 12 modules in it. And I've assigned you module 1 and module 2 and have tell you to submit some screenshots of your completion of that. And as you go along, there's some knowledge test stuff, like 5 or 6 questions that are multiple choice that you can take multiple times if you screw it up the first time. So, should be an easy 100% for everybody, assuming you do spend the probably 2 hours, or probably not 2 hours for this one, maybe an hour for this assignment. Make sense? So start going through that. I'll keep going through my content, and then we're going to merge those two together, and then we'll push on to our normal book and the Python stuff around week 4-ish, something like that. Yeah.
Just kind of curious about Mendix. Like how well does it know with native? Are you able to build on native code to it, or?
What do you mean meld with data?
Like you mentioned, this is a better solution than someone starting off from just scratch with native. Are you able to use this as a starting point and then building off from there, or does this have like a very set number of features?
No, you can definitely, because you can talk to third-party APIs with this. Okay. It's actually shocking how good they do things, how well they do things. And on top of that, they have their own database built into it with a visual modeler on top of that. So you actually never even have to leave the Mendix platform to do a majority of software development stuff. And then if you want to bring in third-party stuff like stock quote information, you can connect it to that. Yeah, I mean, it has its limitations, but as far as a tool that allows non-programmers to write things as if you're a programmer, and as well as acting, as well as having the power that a programmer, having the tools that a programmer needs, which is why I kind of use this as a teaching tool, because it allows me to introduce those high-level concepts that we'll learn how to do the hard way, because we're effectively like car mechanics, right? As a computer science person, we're going to be learning how things work under the hood, not because that's the way we're going to necessarily do things on a daily basis, but because it's important that we understand how the car works in order for us to fix them, not just drive them. This is maybe somewhere in the middle, where let's say you work for a marketing company or something like that, and you've dabbled in some programming, don't have a ton of experience, don't necessarily know how to connect this tool to this tool to this tool, and maybe you're not even sure if you even need this tool over here. This guy gives you kind of a one-stop shop where it has all the pieces that you need and doesn't really require you to have a vast knowledge to build a final product. Makes sense? So I've been pretty impressed with it. I'm going to be presenting a couple of papers at some conferences about it. It's not perfect. They're desktop modeler. So one thing I would encourage you as you're going through this, if you're a Mac user, I would either dual boot your machine in Windows or get a virtual machine like Parallels or something like that and run Windows on your machine. Because the desktop modeler, they have 2 tools. They have a desktop version of Mendix, and then they have a web-based version of Mendix. The web-based version of Mendix is currently in beta, so let's assume you might have some little weird bugs and things like that with it. Having said that, it might be okay. If that's your only option, you don't have a convenient way of getting to a Windows machine for at least the first couple of assignments, you could probably pull it off in the web modeler. But I would highly encourage you to use the desktop modeler, which is only compatible with Windows. Make sense? If you're a little bit more geeky Mac user, I haven't actually tested this, but you might look at a tool called Wine, W-I-N-E, which is a Windows emulator for Windows that allows you to run, or for Mac, that allows you to run, originally came out for Linux, so in Macintosh is a Unix-based system. It'll allow you to run Windows applications directly on top of the Unix-based operating system for the Mac. Might be an interesting little project if that's something that you're interested in doing, but not related to what we're going to be doing in this class. That would be more of a geeky project if you're into emulators and stuff like that. Path of least resistance is get onto a Windows machine, install the modeler, and do your homework that way, or dual boot your Mac. That's usually why I tell folks to, if a student asks me what's the best machine to get as a computer science major, I typically, you start off with what's your budget, right? If you have $2,500 to blow, well, let's talk about a Mac. Why? Not because Apple's better. Fine, the build quality of this machine is going to be better than your plastic-based PCs, but that's only impressive for the first 15 minutes, right? At the end of the day, what does a Mac get you? It gets you 2 machines for the price of 1.7. Right? You have one machine that can dual boot Windows and dual boot Mac, so I can boot this guy into Windows and have a Windows platform sitting right in front of me, and it's pretty portable. and you pay a premium for having that, but at the end of the day, that's what that machine is. If you have $1,000 to spend, I'll guarantee you can get way more laptop on a PC-based laptop for $1,000 than you can with a Mac. A Mac, you get a screen and a keyboard for $1,000, you know, and that's kind of your limitation. But, you know, in any case, get onto a Windows machine or a Windows operating system at some level, and your homework will go more smoothly. Because most of the module is kind of like monkey see, monkey do. You watch a 3-minute video, then you know, below that is kind of screenshots of what you just watched in the video that takes you through. Here's the 7 steps that we want you to do with the modeler to get used to the tool. That's kind of the cadence. Then at the end you hit a button that says mark is completed and go to module 1.2, so on and so forth. Do that for an hour and you'll have your homework done. Submit a couple of screenshots. All right, questions about Mendix at this point? I'm sure more questions will come up as we keep introducing stuff, but have a decent idea at this point? I promise going through this process will make your dive into Python less scary. I mean, it's still going to be intimidating, but you'll only be focused more on the programming language syntax and how it's kind of weird than how do I solve problems in computers. Okay, good.
This will be up on Blackboard?
It's already up on Blackboard.
Already up?
Yep, assignment's up there. The link that takes you directly to the tutorial thing, which is it's actually an intermediate, what's called, I think they call them learning paths or something like that. And it's the one that leads to the certification.
Do you need to create an account with
Yep. First part of the assignment even says create an account. Yeah. You got everything you need, trust me.
Okay.
If you have questions, slap them on Slack and you'll be good. All right, so let's pick up where we left off last time. We were kind of working on our history of languages. And right at the end of the class, we were talking about kind of memory costs and how it's it used to be very expensive. And so really when we think about the nature of computing, things have really drastically changed in the last 20 years. I mean, obviously our computers keep getting faster and faster and faster, and then they started getting smaller and smaller and smaller, right? We kind of kept the same speed. They kept getting into the smaller packages. Now what are we doing? If we kind of think about it from mobile computing, because now we've kind of split, right? How many of you actually have a desktop computer at home, or is your main machine your laptop? So notice probably a third of the room just rose their hand. 20 years ago or 15 years ago, let's say, everybody had a desktop. You may not have had a laptop. So we're moving into more of a mobile society. Now, how many of you have a smartphone of some type? An Android or an iOS device? Something like that, right? So most of us have something, even if it's one of the budget pleaser ones that's running, some old version of Android, we have something that is a smartphone. Now, is this guy a computer? Yeah. In fact, we've started to move towards the thing where you can actually be fairly productive on your phones. How many of you have chosen to use your phone to do something as opposed to a computer because your computer requires you to get off the couch to go get it? It's 6 feet away, but you got to get up because these guys have become problem-solving machines. Now, what trend have we seen with mobile phones, with our smartphones recently? Well, for a long time, they kept getting faster and faster and faster with longer battery lives, right? Have you noticed that the last several years, what's happened? The battery life is maintained, right? So now what have we seen? Bigger, better, brighter screen, same battery life. Now, this is the Galaxy Note 8. I was an iPhone user up until this year. My wife still has iPhone. I write software for both of them, so whatever. So the rumor for possibly the Note 9, Galaxy Note 9, is they're looking at these bendable, foldable screens. So you'll have a phone that's like this size, but if you want it to be a tablet, you just fold it out. Now you got this tablet. I don't even know how usable that would be. But I'll tell you what, it's great to have. The bigger screen is better, right? Because a lot of us anymore, how many of you actually appreciate the fact that your smartphone makes phone calls? Or is that just kind of that's an extraneous feature that isn't even all that important, right? Like if the cellular phone call network went down, it might take you several days to notice, right?
Yeah.
But if your ability to check email went down, or your ability to text or text message might be, that's still using the cellular network, but whatever. You notice those things. So these things are no longer only phones. There's something more than that, right? All right. So now the issue is so the point here is that technology has really changed quite a bit in 20 years. And it really started with where our bottlenecks were. So on our early computers, let's say the early consumer computers where people were actually like normal people were buying them to put on their desk at home, not when they were in, big corporations and stuff like that who had a lot of money, who could afford the premium for them. Good movie that you might check out that kind of talks about that transition. I just had it on the tip of my tongue and now I can't remember it. Came out last year. It's about these like 3 or 4 African American women who worked for NASA. Hidden Figures. Really cool story. So I mean, you got the one side of it where women being taken seriously in industry, but from a computer science perspective, you had NASA first bringing in computers when they were doing all the math by hand before that. So some of these women started learning how to program the computers because most of the other people couldn't figure it out. It was so new that it was intimidating for them. And that kind of just showed that transition to you have these genius mathematicians that worked for NASA who had to get it right, but then they were quickly replaced by computers no matter how good they were. They couldn't keep up with the computers. So there's an interesting technology piece there that it's worth seeing. How many of you have seen the movie, Hidden Figures? 1.5 people. All right. Check it out. It's worth seeing. Very, very good movie anyways. Good story and kind of gives you an appreciation for some of the things that have happened in, certainly American history, but there's some scenes where like the women, because it kind of centered around these 3 black women where they had to like run to another building because that was where their bathroom was, stuff like that. So, gives you an appreciation for as bad as things are today, it's better than it was. We have our new problems now. Okay, but in any case, I think I mentioned last time that a famous person, Bill Gates, Microsoft guy, once said that you'll never need more than 32 kilobytes of memory. That ended up not being a true statement. And really that statement was made during a period of time where 32K of memory was expensive. We don't even, we kind of talked last time about some conversion, size conversion and stuff like that we had to do with the 70 or 60 gigabyte internet over there, right? Is that what it was, 60 gigabyte? Yeah, something. Yeah. So, we kind of added, talked about, what these different sizes and speeds might mean and how fast data moves, but kind of putting it into, a meaningful thing for us. And we kind of noticed that if we are the technology people, so in most of your families, you're the tech person, right? Something breaks or whatever, they call you up and say, oh, I can't fix the router, I need to do something. And whether you know anything about it or not, you know more about it than they do, okay? Yet we just proved last time you don't even know how fast your internet is. It's like the blind leading the blind here. All right, so in any case, we want to have an appreciation for this stuff. But what we take for granted today, you go out and you buy a used budget pleaser laptop that comes with 4 gigabytes of RAM. The amount of memory in that is just astronomical related to what we had. I used the example in 1996. I had a computer that shipped with 8 megabytes of RAM. I added an 8 megabyte chip to it. Now, if we convert 4 gigabytes into megabytes, so 4 times 1024 is 4096, right? That's how many megabytes are in 4 gigabytes of RAM today. We're going to call that the crappy laptops. If you go out and buy a laptop today and you're buying the value ones, it's probably going to only come with 4 gigabytes of RAM. That's 512 times more memory than was in my bleeding edge computer in 1996. I had to wait for them to release the processor. It didn't exist yet. Okay, so machines typically came with either 2 or 4 megabytes back then, so 8 was ridiculous. Right? Then I added another 8 megabyte chip. So your budget pleaser laptop today has 512 times more memory than my bleeding edge computer had in 1996. And I mentioned last time that I paid $1,000. It's actually a little more than that, but let's just use round numbers. So I paid $1,000 for 8 megabytes of memory. So 8 divided by, the other way around, 12,000 divided by 8, I paid $125 per megabyte, right? And we talked about today that you can get a 4 gigabyte chip. Let's just call it $40. Well, we used $30 last time. $30. So we would take 30 divided by 4096. Less than a penny per megabyte. Less than a penny. So even if we round up and say it's a penny, $125 is 125 times 100 pennies. It's 12,500 pennies. Right? So it's more than 12,500 times less expensive today. I guarantee that outpaces the stock market in that same period of time. Okay? That's better than Bitcoin. All right, so memory has, and I mentioned at the end of class last time, this was after memory had already started dropping in price drastically. This is when it was cheaper. So you can imagine if you roll back 3, 4, 5 years from then, that it was even worse. That discrepancy was even bigger. All right. So what does that mean for us as computer scientists? Well, it means that our bottleneck has shifted. So back in the 80s, late 70s, 80s, even into early 90s, let's say, the amount of memory we had on our computer was a very precious resource. Okay? Very precious resource where when we were writing our software, we had to be very careful about how we used that resource because we'll run out quick. That make sense? All right, so last time we started talking about kind of our history of languages. And I mentioned that almost all of the way I like to teach this is that all of our modern languages came from the C programming language. And that's probably a 95% truth. Okay? It's a good basis for us. So what we will see is we'll see some things in our programming languages today that are left over from the time of C. Okay, what I mean by that is we've talked about the way human beings solve problems. We use memory, we ask questions, and repetition, right? That memory thing is where we start off. So I've mentioned that we have this thing called memory. I'm just going to put this right after C. So memory is typically done through something called variables. Okay? Now, when we talked about remembering things, I said all of you know your name, right? So if I say, what is your name? You spit out some value associated with the little memory bucket inside your head that you've stored your name in, right? Okay? That's how variables work. These are name-value pairs that are stored in the computer's memory. Okay? Now, we mentioned last time, or time before that we had two types of languages. Did we mention strongly typed versus loosely typed?
Yeah, budget.
Okay. So we have strongly typed versus loosely typed. Here we go. So strongly typed versus loosely typed. So most of our higher performance languages are strongly typed languages where we have to specify what kind of value a particular bucket was built to hold. Now, whether we're dealing with a strongly typed or a loosely typed, whether as a human we have to specify what's in there, at the end of the day, if we have a bucket that has some stuff in it, at the end of the day, before we can use that, we have to identify the nature of that stuff, right? We can't do math with an ice cream cone. It's not going to work, So an ice cream cone plus 7 doesn't mean anything. So we care about the kind of value that lives in there. Strongly typed languages, which were our earlier, still our modern languages are strongly typed as well, but all of the earlier languages were strongly typed languages. Where as the programmer, we had full control, and really we had a responsibility back then to pay a lot of attention to how we were using the computer's resources. Because that's all the computer is. It's a collection of resources that we're sharing between multiple programs and things like that, right? We got the processor, that's one resource. We got the hard drive, that's another one. We got our system memory, that's another one. That kind of stuff. These are our resources that we have to share. And they're not infinite resources. So in a language like C, which is a strongly typed language, Where am I at here? C. We had these things called primitive types. So primitive types are types built into the language that can only hold a value. Now, what that implies is that in our more modern languages, especially with object-oriented languages, we mentioned last time that we might have things that can hold values and then do some other stuff, functions and stuff like that. All right, so built into our languages, or at the core, are going to be these primitive types. These are things like integers and decimals and stuff like that. And we're going to talk about the core C primitive types here in a second. Okay, so these are primitive types that were built into C. I'll just put it, we'll put it underneath this. All right, so we have something called a byte, something called a short, an int, a long, a char, and these are capitalizing, but they're not actually capitalized, unimportant for our discussion. Then we have a float, a double, and I'm just going to spell it out and say Boolean. Okay, now we're going to start with these top ones. So bytes are signed whole numbers. Shorts, signed whole numbers. Int, signed whole numbers. Long, signed whole numbers. Now what signed means is it can hold positive and negative values. When something is signed, it can hold positive and negative. When something is unsigned, it can only hold positive numbers. Okay? So at the very least, in this discussion right here, we have 4 different types that are all containers built for holding signed whole numbers. Why do I need that? Why do I need 4 different buckets, all capable of holding the same thing? So these are older languages, and this is during a time where we had to pay attention to how much memory we were using. The size of these containers were different. These were 8 bits. These were 16 bits. These were 32 bits. These were 64 bits. That makes sense? So,
sign was holding positive and negative.
Positive, negative, yep.
And unsigned is positive.
Correct. We're going to have an unsigned guy down here in a second. All right, so we had 4 different ways of holding the same kinds of values. The difference was the amount of memory associated with each of those. So then we have to ask the question, well, what's the difference? If I have an 8-bit signed number, so let's jump down here. 8-bit signed number, that means one of those bits is being used to hold the positive or negative value. Make sense? So that means I only actually have 7 of those bits that are used to hold the numeric value. So what is the smallest 7-bit numeric value? Remind me, what's a bit? 0 or 1. So the smallest would be 7 zeros? And what would the largest be? 7 ones. So the value of this guy is 0. The value of this guy is, it should be 127. 255 would be if you had all 8 bits. Now, this isn't a memorization problem. Let's figure out how we got those 2 numbers, okay? Because this is going to come down to converting. I'm a huge advocate of converting between values for computer science majors. All right, you should be able to move between decimal and binary and octal and hexadecimal. And if I just decide base 23 for no good reason, you should be able to do that because the pattern is identical no matter what the bases are. All right, and when I say I'm a big advocate, talk to our juniors and seniors. Conversion questions show up on every one of their tests to this day. No excuse to miss them. Should be easy points. So learn it now, because it's not hard stuff. You just have to understand the pattern. Okay? So, how does this work? Now, we've been doing this math for a long, long, long time. And I'm going to prove it to you, if not this class, next class. This is the ones place. This is the twos place. The fours, the eights, the 16s, the 32s, the 64s. Our number system works the same way. If I give you the number 138, the 8 is in the ones place. The 3 is in the tens place. The 1 is in the hundreds place. This is the ones place. Times 10 is the tens place. Times 10 is the hundreds place. Because we use the base 10 number system. Does that make sense? If we're using the base 2 number system like binary, this is the ones place. Times 2 is the twos place. Times 2 is the fours place. Times 2 is the eights place. 16, 32, 64. Make sense? We're multiplying by 2. We can also look at this as this is the 2 to the 0th power place. This is 2 to the 1st power place. This is 2 to the 2nd power place, so on and so forth. Make sense? So how do we actually do this math? I'm going to go from right to left because it's easiest to do that, right? So ones place, twos, fours, eights, 16s, as opposed to figuring out what the final one is and then having it each time. So I'm going to go from the right to the left. So this guy is 0 times 1 plus 0 times 2 plus 0 times 4 plus 0 times 8 plus 0 times 16 plus 0 times 32 plus 0 times 64. So it's this value times its place plus this value times its place plus this value times its place, so on and so forth. Now 0 times anything is what? 0. So this is going to be a big old fat 0. Make sense? Go ahead.
So is the base the variable of which you multiply everything else?
Well, the base of a number is it represents the number of unique digits. Although digits only is base 10. So the number of unique characters associated with that base. So binary only allows zeros and ones. 2 of them. Decimal allows 0 through 9. 10 of them. Hexadecimal allows 0 through 9. Well, it's actually 0 through 15. But we need a single character. So 0 through 9, A through F. A is a 10, B is an 11, F is a 15.
Okay.
All right, that's base 16. There's 16 unique characters in that alphabet for that number system. Okay, base 4 supports what characters? 0 through 3.
Yeah.
Okay, base 27 supports 0 through 26, and then you have, the alphabet for representing those. So our limitation is really base 38.
Okay.
Because we run out of characters in the alphabet. And we've looked into, you could always come up with your own alphabet for representing things. We've looked into Klingon. There's actually only 22 characters in Klingon. So we hurt ourselves moving from English to Klingon.
Unless we just add them together.
You could do English and then move to Klingon. That's true. It's not a bad idea. So as we need to start representing gigantic bases, that's a true value. That's a true thing. Go ahead.
Does C still use the ASCII American Standard?
Oh, well, what do you mean does C still use?
Like
C does use that. We'll talk about that when we talk about chars. Modern languages use Unicode. Newer thing. Okay, so everybody understand how we got to our 0 here? Now I'm going to steal this dude, so I don't have to type as many things. I'm going to come down here for this guy, and now it's 1 times the 1's place, 1 times the 2's place, 1 times the 4's place, 1 times the 8's place, 1 times the 16's, 1 times the 32, 1 times the 64. And 1 times anything is that anything itself, right? So this is 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64. And there's your 127. Make sense?
Could you say again what we are going from what to something else?
This is from binary to decimal, our number system.
Okay.
So here, if you want me to, this is binary, which is base 2, to decimal, which is base 10. Now, just real quickly, let's assume that we were going from some base 4 number to decimal. All right, so I'll keep it a relatively short number. So base 4 to decimal. Now, base 4 is not actually a base that's very common in computer science, and we'll talk about why that is. Actually, maybe not even in this course, but when you start getting into computer organization and stuff like that, we talk about why our kind of go-to moves are binary, octal, decimal, and hexadecimal. Decimal is because people.
Mm-hmm.
But those other ones have to do with conversion to binary. They make it convenient. So pick your favorite base 4 number. All that's important here is you only use what characters?
0 through 3.
0 through 3. So pick your favorite number that is only made up of zeros and threes. So let's say
132.
132. Okay, we're going to say 132, and we're going to remember that this guy is in base 4. Because that's given information. Because that number could be in other bases, right? Okay, as long as those characters are legal in that base, somebody's got to tell us what base it's in. We make the assumption with numbers in our daily lives that they're base 10, because that's what we typically run into. So if we want to convert 132 from base 4 to decimal, this 2 is in the 1's place. Times 4 is the 4's place. Times 4 is the 16's place. Make sense? So this is going to be 2 times 1 plus 3 times 4 plus 1 times 16, which is 2 plus 12, which is 14, plus 16, which is 28. So this is 28 in decimal. Make sense? And this works for any base. Base 10 to base 10. Waste of time, but works. So let's take your 132 again, right? Was that your number, 132? Yeah. 132, and we're going to say this is in base 10. That's a legal base 10 number. It's made up of numbers between 0 and 9. Okay? And we're going to convert that guy to base 10. We know our final answer will be 132. But we want to see if we calculate it, if it comes out to be the same. So it's just 2 times the 1's place, plus 3 times the 10's place, plus 1 times the 100's place. So that is 100 plus 30 is 130, plus 2 is 132. Make sense? Identical pattern when we're going from any base to decimal. The only time things get a little hit and miss is when we go from a base larger than base 10, where we have to look at a larger alphabet. So I'm trying to think of my favorite. Oh, no, this will work. I don't have to worry about the conversion. I can just remember it this way. So if we do hex, which is base 16, to decimal, which is base 10, So all of these are some base to base 10, right? And my favorite hexadecimal value, BAD. Okay, so hexadecimal supports has the alphabet 0 through 9. So here's the hexadecimal alphabet. Hex alphabet 0 through 9, and then A through F. A is a 10, B is an 11, C is a 12, so on and so forth. Because we need a single character to represent that value. Okay, we're still going to do the math off the 10 or the 11 or the 12, but to represent it, we have this. So BAD is actually an 11. So if we draw a little thing, so this is an 11 followed by a 10, followed by A is 10, B is 11, C is 12, D is 13, followed by 13. That's the numeric value of those three hextets. That's what those are called. Okay, digits are decimal characters. Hextets are hexadecimal characters. Relatively unimportant as long as you can do the mapping. See, this is all trivial stuff. None of us are intimidated by this at all. You're intimidated? Go ahead.
It says like bad, or so I understand how it's like the 11, 10, and 13, but do you add those together? Or just
Not yet. We're going to do the exact same pattern. This is my hex number. That's my favorite hexadecimal number. Bad. Okay? You can pick any word that is made up of 0 through 9 and A through F. I just happen to like that one. Okay? I think it's 2948 is when it come out to. 2980, something like it. We'll see it in a second. So we're going to do the exact same thing we did before. This is 13 times the ones place plus 10 times the 16s place plus 11 times the, was it 4096 place? 16 times 16, 256 place, sorry. The next one is 4096. 11 times 256. Oh, it's 2989 is what it will end up being. So I'm just going to take all that math. I'll paste it in here. There's our 2989. So this is 2989. So BAD in hexadecimal is equivalent to the decimal number 2,989. Okay. Make sense? That one felt a little scarier because we had to do that alphabet mapping, right? An A is a 10, a B is 11. Not a big deal. We just had to remember to do it. But after we did that, was the pattern identical to what we did for all the other ones? Mm-hmm. Identical, right? Go ahead.
So then the 132 base 4 is equivalent to decimal 30.
132 base 4 was decimal 28.
Okay, the math just sucks then.
16. Actually, no. Hold on. Yeah, no.
Yeah.
2 times 1 plus 3 times 4 plus 1 times 16. So 16 plus 12 is 28. Oh, no, you're right. It is 30. My math sucked. See? I was testing you. You all failed. Well, you get a star for the day. You corrected it. You failed me. This was your job. You can't blame this on the hips either, dude. This is all what's between the ears. See, we'll learn pretty quick. When I make a mistake, I did it on purpose because it was a learning opportunity. I tell my upper division programming students, I'm still waiting for my first compile error. I've never introduced a bug into a program I've ever written in my life. It just doesn't happen. Those were educational opportunities. All right. All right, so we like the conversion stuff, fun stuff. I have a feeling, a strong feeling, that you might have a quiz on Friday, converting from some base to base 10. Make sense?
Mm-hmm.
Yeah.
So you might want to study these couple of slides. This one, this one, this one, and this one. They all do the exact same thing, just going from a different base to base 10. So I guarantee your quiz will be, the destination will be base 10.
Mm-hmm.
And the starting point will be some base between 1 and 36. No, 1 in 37 actually. So because that would be A through Z. Right.
Because I don't know
Go ahead.
any Klingon
Is
characters.
it like greater than 16? So like, if you keep going, is it just more letters?
G. HIJK. Yeah, just keep going down the alphabet till you run out of letters. And then, as he pointed out, we'll switch to Klingon. I assume all of you have the Klingon alphabet memorized?
No.
There is going on.
Look it up. There is a Klingon alphabet. It's unfortunate that that's a truth, but there is a Klingon alphabet. Big Bang Theory makes fun of it, but if you look it up on Google, there's an official Klingon alphabet. They got the symbols and everything, as well as how to pronounce each. I don't know if it's a letter or what the.
It's a
like,
character still, right?
yeah. Well, I don't know what the Klingons would call it. Yeah, we'll have to ask them.
Klingons are a race.
So we can memorize the Klingon by Friday. We get an automatic
So let me consider this for a second.
Yeah,
An automatic A for the class or an automatic A for the quiz?
The class.
Hey, I'll tell you this.
Oh goodness.
If you can stand in front of class on Friday and verbally recite the Klingon alphabet, I'll give you a free quiz.
Oh.
that might be a deal.
No, a free 100 on a quiz. This is open for anybody.
This is legit.
Okay, I don't encourage you to take advantage of this.
The full one? The full Klingon?
Yeah, you have to do. I think it's 22 characters,
Okay.
This
is pretty fun.
Yeah.
Do it.
and I'm gonna videotape this.
Yes.
Shit, we got the notebook down.
All right, questions, comments, concerns, bribes. All right, homework assignment is up. It is homework assignment is up. It is due on Friday for those first 2 modules. Bible homework is up. It's due by midnight on Friday. So our normal homework is due before class starts.
Okay.
Bible homework's always due by midnight on Friday.
With the Mendix, you're talking about, you have a link that goes to.
It's on the homework.
Is it going to take us to the web browser?
It's going to take you directly to the module. The module, the very first part of the module, will tell you to go download the desktop thing. It
Okay.
takes you through every step.
I do have a question about downloading the desktop thing. Can we do that on the school? I mean, like the lab. Any of the lab computers? We'll be able to do that.
As long as you can install something. So I'm not 100%.
Okay. Because I wasn't sure about that because my laptop I really don't use at all because it's kind of old and I don't know if it'll feel good.
Okay. Let me know if you have problems, and I can probably remote in and do something, or I'll tell you to go to one of these other machines, one of our VR machines in here.
Okay.
I can remote into and get you on them, but we'll figure it out.
Okay.
This first thing is, let's call it relatively unimportant.
Okay.
You know, it's just to kind of get you into the platform. So if you have any problems, don't get stressed out. We'll just make
Okay.
sure you're working for the next one.
Sounds good.
1 second.